I can fit into.
It's about 15 minutes delay, so you can use one and a half of it. Yes, so let me again introduce, now I will try it, Vásárhelyi.
Vásárhelyi.
Vásárhelyi. Let me introduce him. He's going to tell us something about bio-inspired collective behavior of autonomous drone in swarms. So it will be against swarms. So please, may I ask you for your attention? Thank you. Go ahead.
Hello, thank you very much for your attention on this very hot afternoon. Still, I try to bring you some refreshing thoughts, not partially not related to drones, but or multi-robots, but things in a broader sense. And I will introduce a lot more biological phenomena into my talk. As you see, my affiliation, I come from a university in Hungary, from the Department of Biological Physics. So we started to get into this drone business through the observation of animal collectives, collective decision-making and collective motion, and then we tried to apply these rules to the drones. Also, Comot Robotics is listed here as well. This is a small spin-off company that we founded on already the drone-related part. So this is the university in Budapest. It's a very nice campus. Actually, it would be better to be located at the Technical University. This is more like a basic science university, but this is how life goes. But one advantage of the university is that we are not allowed, but at least tolerated to be able to fly drones there. So we can do our experiments right next to the building, and in the middle you see the proof for that. We were trying to reproduce this little modern sculpture that is in the middle of the university with a long exposure photo of drones. So if I had to tell you in the broadest sense what my talk is about, then it's about the emergent property of complexity. So if you think about any kind of entity or object in the universe, you see that everything is consisting of smaller parts that are simpler than this entity, and they have interactions. So if you think about atoms, they come together, interact with each other, and then create a new level of complexity. For example, molecules that has inherently different characteristics than the parts themselves, or the sum of the parts. And then if you look at the molecules, you put together a lot of molecules, then you start to get proteins, which are not a sum of a bunch of molecules, but a new level, which is totally different. And then you can go further and further into more layers of complexity, and with each layer you get increased complexity with increased possibilities and increased problems as well. So the problems arise together with the increasing level of complexity, and then through proteins you get to tissues, and then cells or tissues, and then humans, and then you can go further or to species and societies and the whole globe we are living in, and this is still just one planet. So this whole structure of complexity is very layered, and particularly from this we will focus on one layer, which is where you have intelligent entities, and you want to see how these entities come together and move together. So this will be the basis of my talk, the collective motion. By the way, this image is also a kind of a collective phenomenon. We were painting it with a bunch of friends together in a self-organized fashion. So we started to paint, and then everybody was bored. We just flipped the whole thing and continued. It's a very fun thing to try, and it gives you the really basics of self-organization, how complexity emerges or patterns emerge in a self-organized way. So from this complex phenomenon, I will talk about collective motion. We have seen exactly some of these pictures. What is really intriguing in nature is that you have these motion patterns in very different kinds of animals. So on these images you see insects like locusts on the top left side, then you see mammals, you see birds and you see fish, and the patterns they exhibit are very, very similar to each other. So it seems like that in these collective phenomena, the individual intelligence of the agents doesn't count that much, or in some ways it's not important. What is important is the interaction between the agents and yeah, how they solve things together. So more particularly, you see, this is a film about reindeer from the north, filmed from a drone. These patterns, what you can see is like one of the most trivial patterns of collective motion. If you tell simple agents just to move in a confined space, the only state where they can find a constant velocity movement is some kind of this rotational movement, and this rotational movement is there in the nature everywhere. So you could see a film by bacteria who are doing the same, and you can see the reindeers doing the same. It's very beautiful, and still in these patterns, the intelligence of the individuals, like these are obviously more intelligent than the bacteria, but what they think about the world doesn't really count. What counts is the interaction between them. In the next image, this is a more complex pattern of collective motion. These are starlings from Rome. There's a very great group in Rome who are studying the motion of these starlings. And what is really intriguing in this, obviously you see a lot of patterns that are, again, emergent, and you couldn't tell that these patterns would emerge from like single birds or a bunch of birds. What you can see is waves of information going through, which means that all the information processed here is local and it's spreading throughout the whole flock. And another thing that is really, might not be obvious, but if you think about it, that you have to admit that it's true that this system is optimized to health. So these birds should do their best to keep the distance from each other and maintain all these formations and be very stable and very reactive at the same time, and they must know it instinctually. I don't know, so evolution must have optimized this system very, very much to be like that. So what we are doing, this is a third example. I really like this video. It's from BBC, like Blue Planet or something like that. It's like a very complex scenario where I counted at least 6 different species who are taking part in some kind of collective phenomena, like birds are diving into the water, catching for fish. The fish are there, they are catching some very small, like krills or something, and then dolphins come and sharks come, and this is crazy. Like the fish should be like really scared here, like that enemies are coming from the sky and from below, and everybody is exhibiting collective patterns, and it's beautiful how you see all these birds flying in a flock, or I mean like diving in a flock or swimming under the water. And then also like this could be some kind of a challenge for the next thing to do these kind of flockings, to first start in the air and then go underwater, continue there, but have like large ones and small ones and catching each other. So it's really beautiful. I could see this for hours. So you can see that with these kind of collective things, you can do very, like animals can do like very, very difficult tasks. They can collaborate very efficiently, and still in all these collaborations, you can see the same patterns and same kind of motion, basics of their collective motion. So it gives you a hope that there is a simple way to describe how this motion is done. So if I want to summarize this, this was kind of the biological part. There are some key descriptors of collective motion. What are important? The first is that these systems are, in statistical physics, you call it non-equilibrium systems. It means that agents are somehow self-driving. They have some kind of inner power to move, and if they let them go, they don't stop in like equilibrium physics, but they have some inner force which keeps them going, and this gives a very different dynamics from equilibrium systems. I've talked about this, that all these patterns, it's called that they are universal. So you can have simple flocking models that can be applied to ants and bacteria and humans and mammals and cells migrating in your tissues, and still the same kind of laws are valid for all these. Important aspect that you have local decisions and interactions, and you get global behavior and global patterns. You get kind of simple rules on the individual level, and then you get very complex dynamics of this whole system. So that's what I said, that the emergence means that complexity increases, and the problems and the advantages are numerous, both. Yeah, so local decisions and interactions between the entities. Obviously, these whole systems are very decentralized, so there's, in nature, there's no such thing as a central computer, except for God, maybe. But so everything is decentralized. Every computation is done on board with local sensors and local brains and interactions between the autonomous agents or living animals. And I've told this, that it's optimized. The optimization method of nature is always evolution. So it's worth to learn how evolution is doing this. And complexity is emergent. So you don't expect that to come. It just comes out of nowhere just because you have a lot of agents. So we started to, first, not as robotics guys, but as physicists, we started to investigate some of these systems to understand more how this collective phenomena is working. So what we did first is we created little GPS trackers put on pigeons. Pigeons are good species because you can catch them, they are tame, so you don't have to have like radio transmission on them. You just put the loggers on them, they fly and then come back to the nest, and then you take it and download the data. So at the time when we were doing this, like 10 years ago, we had like 13-gram miniature loggers, which was kind of a world record, and we could put it on 30 pigeons, and then we analyzed how they are flying together when they are moving in a flock, what you can see everywhere in the towns. It's very worth to watch them. If you want to do multi-robot systems, just watch the animals as much as possible. Pigeons are very nice for that, and try to analyze how they move, how they make decisions. So one intriguing thing about pigeons is that we measured that there are hierarchies in the pigeons. So there is a dominance hierarchy on the ground, so pigeons know who is the strong guy and who doesn't let the others go to the feeders, for example, and who is picking the others more or fighting with the others more. And so there is a strict hierarchy, what we know of, but when they are flying, there is a totally different context-dependent hierarchy, which is based on the navigational skills. So in the air, there are pigeons who are leaders, and there are others who are followers, and there is a hierarchical structure about the leader-follower relationships. So it's something that was not expected, but came out of the data, that this hierarchy is actually there, and this is good to learn, that if you want to make many agents move together efficiently, that probably hierarchy will be a key question here. Another interesting thing is there was one video in the previous talks when formation was going to be kept when the ground-based robots were going on a figure-8 shape, and there it was made that the agents were trying to keep like a formation which is kind of a rigid body. So if you are turning with multiple agents, you can do the turns two ways. One way is to have it like a rigid body, and then the relative positions relative to the direction of the motion will remain the same, which means that the ones on the outer side will have to move faster and on a larger trajectory, and the ones inside will have to go slower. So this is actually not very convenient many times when, for example, you are flying, it's not that easy to change your speed. So another type of turning is when the leader-follower relationships are changed. So you are turning like this, that the leaders, spatial leaders will be different. Everybody's going on the same trajectory length, so the same speed, but the whole thing will kind of rotate. And we were analyzing the pigeon data, how they are doing this, and it turns out that they like to keep this rigid body turning, but if the turning curvature is too high, so they have to make a quick turn, then they just cannot keep up with that. They cannot speed up or slow down, so they just rotate and then rearrange and go forward. So this is just an example aspect of what you can observe. This is like a fun example of a two-level hierarchy of collective motion. These are wild horses in a wild reserve in Hungary when we are trying to, it's a national park where they are trying to like have a very rare, almost extinct wild horse species come alive again in a huge territory. And actually in the horses you have like harems, like one big male guy has like I don't know, 10 wives, and then there's a harem, and they go together in a very strict formation. And then there is interaction between the harems as well. So you have these two levels of hierarchy in the motion, and all the harems move together, but within the harem there is like a tighter coupling between the agents. So it's very interesting. And this is a recent article in Science from one of my colleagues in the lab. This is they were investigating the collective thermal-link behavior of storks while they were migrating from Europe to Africa. And actually there were some researchers who went down with the storks all the way to Africa, and they downloaded the data from like 1 kilometer away all the time. They have like the total track from all the migration, but it's very interesting to see that when they have like a local thermal, like a hot air that is going up, what they use not to make to avoid the need for flapping their wings, so they just go up with the air and then glide. So from the first 20 minutes of thermaling, you can tell who are the good flyers, who are at the top of the thermal, who can find the thermals more efficiently, and who are the followers, who are not that efficient and somewhere at the back, and then they have to follow the others. And from the first 20 minutes, you can predict whether they will be able to cross the sea and go down to Africa, or they will stay in Spain and feed on the trash there. So it's very interesting, and it also means that the very details of how skilled you are, how experienced you are in these collective situations really means something. So if you are really good, then you will be able to go across continents, and if not, then you will be tired. So very tiny differences in the optimization mean a lot when you think in large scale. So after all these studies about natural systems and biology, ethology, and statistical physics together, we decided to build our own drone flock of artificial agents who are capable of doing something similar to these systems. So we were thinking about what are the main structures that we can kind of steal from nature, and one is the collective control, so basically the flocking algorithms, how the entities in nature are doing these collective motion patterns. The second one is the optimization, so if we have complex systems, we always use evolution as the optimization. I will tell you why. And the third one is this structure of complexity, what you can see that, for example, hierarchy is something that is a very powerful organizational law in large systems, and many times if you want to control a large system then you need hierarchies, and it's very important to understand how hierarchies work and how they emerge from nothing. So I will talk about a little bit of these three things, how we did it with the drones. So the idea was to create a flock of drones that is autonomous and decentralized. We have seen the great work of Martin and his group here, who are doing like fully autonomous systems. We were not that strong, or not that, how would I say it? So we are a little bit scared of doing full autonomy, so we decided to use GPS instead, because we wanted to concentrate on really these statistical and large-scale aspects of this whole thing. So this is the only cheat in our autonomy, that we use a global positioning system Otherwise, all the computation is done on board on the agents. We would like to do something that is truly scalable, both in size of the system and also in the speed of the system to some extent. And what is really important here is that when you do multi-robot systems with the mindset of having one single drone first and then trying to extend this to 2 drones and then 3 and then 5, like how the ROS is developing, then you just cannot take into account all the dynamical aspects that emerge in systems when they get large. So when you start from statistical physics and hundreds of thousands of particles, and then you want to reduce that to maybe like 10 or 100 or 1,000, then you already know what to expect when you have really a large number of agents. So it's really important, if you really want to have a lot of agents, it's worth to take the time to understand how like large-scale systems work, because there are a lot of interesting things that you wouldn't expect. Okay, we were going for outdoor systems, partly because it's GPS-based, partly because that GPS works, partly because it's more universal than a Vicon system. And what is really important that outdoor you have communication delays, you don't have like such an update rate as on a Vicon, and you have all kinds of noises, you have wind, so these things will just ruin all your first efforts to do multi-robot systems. And of course we want this whole flock to be controllable as kind of a meta unit, so you have high-level commands, what you give to the flock, you tell them what to do, and the way how they do it will be their own decision. So it will be a self-organized system. And of course, the main goal is to have practical applications where we can use all the knowledge or the system characteristics, what we can learn here. So, and this, I also wanted to show this, as Amanda, that the largest swarms today that exist are in the show business. It's really interesting. Like Intel is taking the world record now with 2,000 drones, but there is a Chinese competitor with almost 2,000 drones, and they are fighting on the numbers. But in all these very large systems and in show business, these are all pre-programmed trajectories, so the agents don't necessarily know about each other. They look like a swarm because they are programmed to look like that, but there is no true autonomy here. What we are trying to do is much smaller in scale, maybe 10 or 30 or 100 of agents, but with kind of full autonomy that is not pre-programmed, but that is decided on the spot. So if you want to do this, what you need hardware. Of course, you need some kind of extendable drones, whatever you prefer. Actually, you need some kind of real-time computing. We are not using the Nuke, but a smaller one, which is like either an Odroid or a Raspberry Pi. These like very small computers are developing at such a rate that by now it's like really easy to put a lot of CPU or even GPU on the drones and just attach it, and then you can do all kinds of high-level stuff with that. You need sensors. I've talked about this, so we use GPS as a positioning. Of course, if you have a global position for all the drones and you want them to know the relative positions from each other, you need to communicate that. If you do vision, you already know the relative positions. If you have GPS positions, you have to send the GPS packets to each other. So everybody calculates their own position, and then we have broadcasted wireless, like in an ad hoc wireless network in which we just send status packages around, and then the drones can know about each other by these packages. Oh, sorry. And of course, we don't use Gazebo, but we developed our own simulation framework in which we can run a lot more agents and see all the effects of these collective phenomena. And you need some kind of flocking algorithms that will make our agents fly together in a smooth way. And of course, what is really important that the first time you're not controlling a single drone with a controller, but you have multiple drones, you have to be prepared for all kinds of like fail-safe situations or error situations. And you have to be prepared how you can handle these autonomously. So before you do your first flock fight, you have to know how to land in emergency automatically if something happens. You have to know what to do if the battery fails, what to do if the GPS fails, what to do if your PT is mistuned. So this is probably the most difficult thing, that you have to think in advance to a lot of things and avoid situations. And of course you cannot react to individual failures, so the system has to make all these fail-safe decisions on their own. So this is a very important part of the multi-robot development. So these are drones that we use. We build them ourselves. The specialty is that the main body of the drone is made of wood. I don't know if anybody else is using wood as a drone material, but since again we are coming from statistical physics and we wanted to go for many agents, we had to like reduce the price as well as much as possible. And of course we had a lot of crashes at the beginning, so we had to build our own drones to be able to repair all the parts. So we also use the PixHawk system. I was thinking about, when you told that you're using the PixHawk, that this is also a collective phenomena, like a collective voting system, what kind of autopilot and what kind of communication and etc. people are using, and if many of us are voting for PixHawk, for example, then it will be developed more, and then it will be a stable system. So by now I think it's like really reliable, and we are really satisfied with it. Okay, so companion computer, I talked about it. With the communication, we just use like very simple Wi-Fi network, and we do everything in C and Python, and through our high-level proprietary control framework, what we call flock control. The realistic simulation framework. So there are a lot of simulation frameworks out there which are very nice and very detailed, and give you a visual, not very nice user interface, but we wanted to like have a very simple one that is optimized for these flock level things. And so it's kind of an agent-based modeling system which is optimized for this flock levels thinking. We have some kind of a graphical user interface, but it's like really very minimal. The agents are just simulated as little dots, and maybe like a circle around them as their communication range or size, but they are really like dots in our simulations, simplest agents possible. But in the meantime, we can do our simulations with feasible execution or almost real-time execution times for up to 1,000 agents, which is really nice. And of course, we run them on parallel computers if needed, and there is an optimization module in them, so we can just define a fitness function and run like on a computer cluster 10,000s of simulations, and then some good parameter setup will evolve, and then it's very convenient. The simulation framework we use is not, I have to admit that it's kind of not a professional software. It's not the most beautiful code, but it's available on GitHub. So if you're interested, you can download and try it. Why is it realistic? This is the core thing is that in it. So one thing is that we use a dynamic model in which we try to input all the things that just destroy the nice simulation. So we have delays, we have limited refresh rate of the sensors, inertia and limited acceleration. And if you have all these, then it makes this whole flocking thing much harder to do. But if you want to go outdoors, you have to face these problems. And we also have models for the different sensors. So the input noise, the output noise, all kinds of communication limits. So we were trying to like, fight with ourselves and make our situation much more harder already in simulation to be able to be prepared for the real-time outdoor experiments. So if you have a simulation framework, then you have to do some kind of problem statement. So we work in the velocity regime. This is very convenient with the PixHawk. You just have to define like a desired output velocity at every timestamp, and then the PixHawk itself will do it, and you can prepare this prepared velocity on your high-level computer based on all your decisions or inner states that you need, and then the PixHawk will try to keep up with this velocity, and you can do these updates. And if you do like position commands, it's not good because your motion cannot be fluent enough, and if you want to go for accelerations, you need a much higher update rate, so it would be more precise, but in a way, but if you don't have accurate and fast sensors and fast loops, then like velocity is kind of a good compromise in between. So what you can see here is that every timestamp you update your velocity. This is like the most simple realistic model of what we use. So there is a characteristic time, tau, under which if you have a desired velocity, your system is exponentially like trying to keep up with that. And so you update your velocity, and you always add the noise term, what you see on the right side, like a basic noise term that just makes the whole thing a little bit stochastic, which is important. And so your main goal is that you need to define this desired momentary velocity at all times in a way that you have the flocking terms, which are kind of the pairwise interactions between the agents. So these are all the terms that are coming from this collective phenomena. You have to combine these with all the things that you want to do with the drones individually. So if I have a drone who wants to go from here to there, this is like an individual task, but if there are many other drones here, then in the time by which it starts from here to there, it has to interact with the others and avoid the collision, etc. So it has to optimize for these two things, not to interfere with the others, but in the meantime, do its own task as efficiently as possible. So this is the tricky thing, how you combine these individual level and group level things. And so we heard about the flocking algorithms, which comes from Reynolds, from the Graphic Design Society, and it comes from my professor, actually, Tamás Vicek, who wrote the first statistical physical article in 1995 about the collective motion and the emergent different phases of motion and the effects of noise that on these non-equilibrium systems, and it's actually a very famous article, and this is where the flocking algorithm was first used. So as we heard, there are three different interaction terms. If two agents are too close, they have to push each other away. You can experience this also, for example, if you are in a concert, your repulsion range is very short, but if you are like queuing in the underground, then you have like a definite repulsion range, and you don't go very close to the one in front of you, and you don't go very far. You just keep some kind of a convenient distance. So, and if someone is approaching you, you just step back. So this is repulsion. If you want to be on tonight's party, then you have to come. So this is kind of obvious that if you want a collective, then you have to stick to the group, and you have to you need some kind of long range attraction, and a very tricky thing is that this velocity alignment in the middle, which kind of synchronizes the motion. And if you think about this, repulsion is always an excitation to the system. So if there are two agents like this, you bring them together, then it means it is the same as pushing a string. And then it will have some inner force, and then it will push the agents away. So repulsion is exciting oscillations, so it's a very bad thing when you have a stochastic system. Alignment, on the other hand, is kind of trying to reduce the velocity differences between the agents, so it's kind of a damping medium. It's kind of like friction, or it gives you some kind of over-damped dynamics, because it means that you have to align your velocity with the others. It means that you have to reduce the velocity difference from your neighbors. So it stabilizes the system in the meantime and reduces the oscillations, which is very, very useful. And actually, this will be like an essential key if you want to make this whole thing stable, because if you do these Reynolds flocking in a computer simulation when everything is idealistic, then it works beautifully. But if the environment gets much more complex, then your system has to get more complex as well to exhibit the same simple behavior in a way. So it's I think this is a very important thought. It's kind of hard to describe. But if you, for example, listen to like very sophisticated music, for example Bach, then you feel that it's like all these melodies are coming very naturally, and you feel that you could even tell what is the next note, and it's very, very harmonic. And this is because there are two things behind. One is that you need like a lot of training, like you have to, like the musician has to reach such a complex level that the performance or the exhibited behavior will look simple again. So the melodies kind of look simple or natural, but there is a lot of exercise behind that. And if you want to do the flocking well, it also means that you have to do a lot of exercise, and you have to get rid of all the problems that emerge in a complex system. So what are your enemies? The enemies are the delay. It's a very important thing. If you have delay in your control loop, you will get chaotic oscillations. There are all kinds of noises. You have inertia. You cannot accelerate your agents quickly enough. There are communication errors. So you have to treat all these systems well if you want to have a working system. Second. So let's start with a very simple flocking model. That's what we did in our first article, what appeared like in 2014 with 10 drones. You can have like a string-like Ripajan, which is like a linear term. The closer agents are, linearly, the higher the force they feel by which they try to like avoid each other or actually hear the velocity. So you can have, this is a very simple Ripajan term. You can imagine friction or alignment as, you can imagine alignment as the viscous friction, for example, in hydrodynamics, that as you see, you are trying to, you sum for all agents the difference between the velocities divided by the square of the difference between the positions. It means that the higher the velocity difference you have, the higher some kind of anti-force or desired velocity term will emerge to reduce this velocity difference, and the closer the agents are, the higher this whole thing will be. So this means that this is kind of an analog to viscous friction. It means that this is how, like in hydrodynamics, the different particles go together smoothly, because locally they don't have, they can have only very small velocity difference. And it also reduces the oscillations. And then you can have a task term in your whole thing. Oh, on the top you see this shield thing. This can be introduced. I will not talk about it too much. If you have walls or obstacles, you can, in this framework, you can treat them as like virtual agents, and then you have the same repulsive and alignment forces with the obstacles as if they would be like another agent, and then you just simplify the whole equations. And then you have a task term in which you have to define your task individually or collectively. For example, if you want to do formation flights, you can split your task term into two parts. You can define some kind of locally measured center of mass, and then you can define the task as like an interaction between moving the center of mass again around and having some kind of relative movement around the center of mass. So this is like a simple approach, and then some things emerge, what I've talked about. So I will try to show you some videos which show some of the problems you experience when you start to build these systems. So probably you heard about this drone attack against the president of Venezuela like a half a year ago. And from the collective motion point of view, this is a very interesting video. What you have to observe here, how the crowd is moving away from this explosion. So people are trying to protect. You see, they start from here, and the information goes very slowly. So I will show you once again. Look for the crowd. So the information is here, now it's here, now all the people are knowing it. So the the information spreading in such a collective is very small, very slow. Everybody knows the information from the neighbors, and it travels from neighbor to neighbor, which means that all your effects or all the changes in the direction the whole flock wants to make takes time, which can be a big problem. You have to take into account this. Another example what shows you some of these emergent collective phenomena is the self-excited oscillation. So in this experiment, it was done a long time ago. The drivers had to just go with 30 kilometers per hour around in one dimension. And what you see is that you get like so-called ghost traffic jams that emerge due to the reaction times of the drivers. So if they're not doing this whole thing perfectly, but one driver starts to stop a little bit, brake a little bit, that the one behind will feel this with a little delay, so it will go closer, and then it has to push the brake a little bit more, and the third one will feel this again with delay and has to push the brake even more, and then the fifth or sixth car will just stop. And just let's look at that again, because it's really important. And you see these waves of stopping cars going the opposite direction than the cars. You see it's now somewhere here. These are already stopping, and this is again a collective phenomenon that emerges only when you have a large size and when you have delays and some kind of excitation or self-drive. And this gives you chaotic dynamics, so it's very, very difficult to handle if it emerges. Like in Hungary, there is one very popular highway that is going to Lake Balaton, which is like a famous summer location, and from the big city, Budapest, all the people are going out on Friday afternoon on this highway to Lake Balaton. And every time there is a police car standing just somewhere on the side, or they are not doing anything, not controlling anyone, but they are there. It means that people will stop, push the brake a little bit, and this means like 2 hours of stopping jammed crowds. Really like 2 hours just from these very small things that the police car is standing there, or something is taking the attention away. So this is a collective phenomenon that has like a very strong effect on our whole society, and it's like the people who are working on the fluent flow of traffic have to struggle with this a lot. So if we use our simulation framework and we implement these very simple rules and we introduce the delays and the noise and the inertia and everything, and like here the task is just to go to a point and stay there with a flock, not even move, just stay there. You see these oscillations that are emerging from these delayed communication. So you have to design a system in which you can tolerate these oscillations and they don't get exponentially large. So for example, you have to have you shouldn't have too strong repulsion. You should have the alignment at a higher range than the repulsion, so that if the repulsion just pushes the agents away, the alignment on a higher distance will stop the agent. So you have to, with parameter tuning and a smart selection of these flocking terms, you have to make sure that your system stabilizes and is not sensitive to all these disturbances. And anyhow, we were managed to, in 2014, we were managed to do our first systems of drones that were exhibiting some kind of autonomous behavior. So they could like follow a leader. It's only a 2-level hierarchy, not like a complex hierarchy such as in birds, but at least they could do that. This is like a visualization of real flights. They could do a formation and go together and keep the distances and not get oscillatory. We could do like very basic formation flights. These are also like visualizations of real experience. Unfortunately, it's really hard to make good footage on drones because they are very small. We could see on your videos as well. So many times it's better to do a visualization where you can enlarge the drones, but then nobody believes that it's real. So it's a problem. Anyways, based on these rules, you can do all kinds of formations. And what we tried also in 2014 is to do flocking in a closed area. If you have fish at home, you know that they are really efficient in this. They have a fish bowl, it's limited. When the flock goes to the end, they just turn around and you never see oscillations. But when we first did it, you could see that at the turning, there are a lot of oscillations emerging because the ones who feel the forces on the wall, they also feel the push from the back, and this creates some kind of discrepancy, and then the density increases, and then the repulsion starts to make it oscillating, and the same thing can be very dangerous in for example, stadiums. There are a lot of death accidents in all the places where many people come together, because the ones at the back will just push a little bit, but the ones in the front next to the walls will have this little push, so it will be excited, and sorry, I have to drink a little. So actually in football matches there are a lot of death accidents due to this, that the density increases so much that the local pressure is just so high that the people push the others to the wall, and then they die. And my most of Maastricht, they were investigating these panic situations specifically where people are not thinking too much but going at the same direction, and where all these things happen. And from the results of those articles, they are now redesigning many places where there are a lot of people together. And for example, if you put like just columns in the middle of large areas where in front of a door, then this helps to avoid the increased density, and then people don't die when they want to go out from a shopping center, for example, on Black Friday in America. There are also death accidents there. From these oscillations, we wanted to go one more step further from this, and we were trying to think about how to define our equations to have like a more elaborate and more efficient alignment term. So we're thinking about what is the expectation from this alignment term. The first thing is that it should be local, so it should be an interaction force between the agents. It should reduce the velocity difference between the agents to make them synchronize. It shouldn't dominate repulsion, because if it just synchronizes the whole thing too much, then the repulsion cannot act on the agents, and then they will slowly but crash each other. So it should reduce all the oscillations, on the other hand, that are induced by the repulsion. And what is really important, that it should work on large velocity domains as well. So if two agents are very quick, then they have to somehow start to align at a higher distance. Based on what kind of algorithm you are designing, you can have specific requirements. So if you do flocking, the alignment is not only local, but it is also global, because you want the whole system to go to the same direction. So you need some kind of collective decision where the whole system is going. But for example, if you're doing traffic, then you need still local alignment to avoid the crashes and the oscillations from the repulsion, but you need the agents to be globally independent, because they are going to different directions. So it's not trivial how to do it, and what is really important is this velocity dependence. So if you look at these curves, the one in the bottom is the stopping distance. So if you have some kind of a braking curve that makes the agent stop in front of a wall or in front of another agent, then the higher the velocity it has, the earlier it has to start braking. So the braking distance of a little drone is obviously very different from a big aircraft that is starting its descent like 1,000 kilometers away, or I don't know, like 200 kilometers away. So if you have high velocity, you have to think more in advance to brake and to slow down to be able to avoid crashes to something. So it means that your alignment, which is a local interaction, also has to scale with the velocity, and it's actually not that local if you want to do it properly, if you have very high velocities, but there's nothing you can do against it. So this is really important, that the higher velocity you have, the higher velocity differences you can have, and then the larger communication range you need in between the agents to be able to treat these velocity differences and reduce this. So we are getting back to these terms, the flocking terms, and this is what we define. So on the X scale, you can see the distance between agents, and on the Y, you can see the velocity or the velocity difference. So the blue line is the repulsion. We can stick to this linear repulsion. The closer the agents are, the larger force they exhibit, and the larger velocity they are pushing each other away. But this green line defines some kind of a maximal velocity difference at a given distance that the two agents can have, and then we can redefine the alignment term in a way that all what we need is to bring the velocity difference below this green curve. So for example, if one agent is at that position up there at the distance of 16 meters, then the maximum allowed velocity difference at this distance is that green curve, because that's the curve on which, if the agent goes, can stop. So we have to get rid of all the velocity difference above that. And so if you define the alignment based on these rules, which is not that local, but because it's dependent on the velocity difference, on the velocity difference as well, you get much better results, and also you can still be under the acceleration limit of the agent. So okay, and I was already talking about this, that since we are increasing the complexity of our model and we have new terms in which we have more parameters, there are, for example, in our current models, we have like 10 or 11 parameters. It's really difficult to optimize a parameter space with 11 dimensions. You cannot do a parameter scan on it because it's too much computational power. So you need some kind of optimization, and since it's a stochastic system and you're simulating, you cannot have like analytic methods to do the optimization, but that's where we bring evolution in, and it's also a very important concept that if you have a complex system which has a lot of parameters, then the system itself is not working. So if you have a brain, the brain itself is nothing. The brain is only functional if its parameters are tuned well. So for a kid, it takes like, I don't know, 10 or 18 or 20 years based on what you want to do to train its brain to be able to do different things with it. It's one of the most complex systems we can have, and it takes a lot of time to tune it. But the more complex systems you have, the more effort you have to put into tuning your system to have a model and an instantiation of the model with good parameters, and these two things will give you a working framework together. So this is another side effect of complexity. The more complex systems you are doing, the more optimization is needed for it. And here comes evolution, which is a stochastic optimization method. So there's no guarantee for a global optimum, but still it's kind of the second best optimization method for all kinds of systems, because it's first of all, because it's very efficient and it's not very dependent on your parameter space dimensions. So you can have hundreds of parameters, right? Like in nature, there are all kinds of things you have to optimize for, and you can take them together. And so its complexity is not growing with the number of parameters. And it's kind of universal. They say that evolution is the second best optimization method for all problems. So it's stochastic, so it cannot be the best, but it's usually good enough. Nature uses it. It's good that we have bioinspiration, and it's very simple. So all you need to define is how you call what is the state when your system is working well. So it means that you have to define a fitness function. And so for flocking, let's go through what you need. You need, if you want a synchronized collective motion, you need some kind of flocking speed at which you want your agents to travel, so you have to bring your average velocity close to that. You just measure all the velocities, and you have an error term based on how much it alters from your flocking speed. You need like connected clusters, otherwise you don't have a big flocking system. You have to maximize your velocity correlation, which means that all the agents are going to the same direction, so they are synchronized. Obviously, you have to avoid collisions, and you have to avoid collisions with walls or obstacles. So this is all if you have a fitness function in which you put all this in, and you run it, and then you get from the evolution good parameters, and then you can go out to the field and test it with your flocking algorithms. So in the meantime, we did our magic dance and increased our drone fleet size to 30 drones, and this is the result from last year, which appeared on the cover of Science Robotics. This is the old algorithm where you see the trajectories of the drones. You see that when they are going to the wall, they split, and the trajectories are not that optimal. And on the right side, you see the new algorithm with much higher velocity correlation, and this is a long exposure photo on which you see the flocking motion of the drones with 30 drones. And by the way, on this image, which was on the cover of the newspaper, if you observe this it's funny that it appeared as a very good solution for flocking, but the photo actually is about oscillation. So if you look at it, you see all these curves that are going like this. It's because when we start the drones, we are really lazy to put them like too far away from each other, because then we have to walk a lot with the batteries, so it's a very dense flock. But as soon as they rise up with individual and they start to like switch on the flocking terms, all the repulsion just quickly just pushes them like away, and the ones in the middle will start to like do a little bit of oscillations. But if you follow the lines, you can see that then it stabilizes and settles down, and then there will be smooth motion. This is again a real flock flight, and the visualization from it, we can, with these algorithms, we could do like very smooth motion of 30 drones. Even we could input like virtual objects defined by GPS coordinates, because we don't do vision, but we simulate like objects instead, and then the flock can split and go around objects very naturally. So if you look at these patterns, they are kind of similar to what you see in nature, that it has some kind of this natural appearance. And also what is important, that here the speed of the drones is already higher. So we did experiments with 8 meters per second flocking speed, which is like, it's already kind of scary when 30 drones are just passing you by with 8 meters per second. This is a short video of the flight. You can see that the motion is like, there's only like decentralized communication between the agents. The motion is very smooth. They have these virtual walls around them on which they just stop, and they start to go another direction, and so this looks good. But again, if you put this system into a simulation and you increase the drone number even more, for example, this is 30 drones and much higher speed, and you will see some parts with even higher drone number and speed. You can start to see these density fluctuations. Again, if you have a larger flock size, then this is a new phenomena that comes in, that due to the big system size and these emergent pressures, the density on the walls where they push each other starts to be very high, and it means that oscillations start there. And if the density, so this whole thing is not scalable really with flock size. These are 300 drones. It's actually working quite good. So it's like almost 100 kilometers per hour, and they are doing it well. But this is kind of a cheat also, because if I remove the objects from the middle, then the densities will be too high because it's a large area and all the drones come together that they just go out and crash. So for example, this thing doesn't work without the obstacles. The obstacles actually help not to decrease the density. So what can we do? We can go back to the nature and see and look at it again and again and try to find it out how these birds are doing. That if you look at it, you see that the density is kind of like completely stable. And what you see when you see them more black and more transparent, it's only because they are rotating, and then you see a different size of the wing. But if you analyze the data, then there are like very small density fluctuations as the information is spreading, but basically they are doing it very well, and it's very intriguing that the information spreading in these flocks is very quick, and this is kind of the key what we are working on now, and hopefully we'll have a new publication within a month or so, at least submitted, where we trying to use the hierarchy and try to create a very quick and active information spreading within the group to make the back of the group know about a wall in the front well in time to be able to avoid in time. So this is the next step, yeah. And also like hierarchy is the other direction where you can go, what you can use in such large systems to make it more efficient. Okay, so now we have kind of stable flocking terms, what we can use as the base of our algorithms. So then we can start to build like individual tasks on top of this. We use the flocking terms as kind of a fail-safe system that you don't have to care about. You have the terms there. You can define individual things for the drones, and when they're close to each other, then they will avoid the collisions by themselves. This is a convenient way to treat the problems. And the first task what we wanted to give to the drones is a traffic algorithm, just a general traffic situations when you have many agents in a coordinated airspace, but with individual tasks. So the task is not to synchronize the motion, but to go efficiently to your target destination while others are going, and then you have like collision courses. And actually, it was not this conference, but I was just going to another conference on the airplane, and I got a napkin with that on it when I was talking about this traffic scenario, and I was started to like shiver and sweat if the company is like thinking about the motion of the airplane this way, because like this is kind of a collision course that is really, really scary, and this is another one which will go to a collision. So if you work too much on something, then everything will look and with that color. Anyways, so this is the situation. Again, people which are part of nature can do this very efficiently. Everybody has a individual task to go somewhere, and they don't collide, they avoid each other, and they do this. You can see that it is, you can measure, but you can also see that it's very, very efficient. So you can actually use the same flocking terms and with some little modifications on the task-specific aspect of the thing, and then you can create like just emergently from these terms what we are using, you can create many interesting traffic situations. For example, if you have like 2 points and you have to like carry a lot of medicine, or I don't know, like sandboxes to fight the water, you can have this simulation where agents just have to touch a point and then come back, and then you have this emergent lane formation kind of thing, which is again a complex emergent phenomena. You can have like, you can simulate these high density junctions, for example, for smart city, high density autonomous traffic in the future with the same terms, and this is it's a simulation, but it's a decentralized simulation, so every agent just watches all the agents around and exhibit these flocking terms with its own task-specific term, and then they do this. And it can be a very useful system for decentralized airspace control as well. So specifically now, as the drones appeared, it's a very big problem for airspace coordination that the number of aircrafts in one segment of the airspace is increasing, and people have like limited capabilities, so they have to train a lot of airspace controller who are watching like big screens and telling the airplanes where to go to avoid the collisions, and it's very, very expensive, and one person can, I don't know, like have a segment with like 7 or 8 maximum 7 or 8 aircrafts, and up like above that, it's kind of impossible with human brain to see what are the best routes for each other to avoid all kinds of conflicts. And with these kind of decentralized algorithms, you can easily treat hundreds or thousands of airplanes together and just suggest, for example, in a semi-autonomous way, suggest the best collision courses based on autonomous things. If you want to do like very efficient traffic, you can also like play a little bit around with the flocking terms, but use the same kind of concept, but change the terms a little bit. So for example, you can have the repulsion in an anisotropic way. So if two agents are going against each other, they shouldn't bounce off like this, but they should be like kind of like this, like having no having some kind of anisotropic repulsion that pushes them away and not against each other. So you can also have select the alignment in a selective way, so you don't have to align to the ones behind you if they're going somewhere else. They shouldn't push you that way to reduce the velocity difference. You should align to only ones that are in front of you and going to the same direction. So this is another modification. What is really important is that if you want to avoid all the difficult scenarios and situations that emerge in complex systems, you have to define your individual tasks as smoothly as possible to prevent going into this situation. So for example, if you don't want a car accident, be very patient and always keep the braking distance. If you do that, you will not die on the streets, I can guarantee you. Most of the car accidents appear because people don't keep the safety distance, and then they get into situations where they have to push the brake too more and the acceleration is too low. So you have to avoid, or you have to actually prevent the collisions by thinking far ahead and avoiding the risky situations, which means that you have to be patient. This is something that we learned from this, that if you design a flocking or traffic system in which the agents are not pushy but patient, they are actually much quicker. So it's really funny. And also, if you have the same target, you again have to be patient. So you have to stay in a queue and wait for the others to go there, because if like you can see it on children as well. You put out some candy and you tell them to eat it, and then everybody will go there and nobody will get it because they will fight. And if you have a queue and they go one by one, then the overall flow of the traffic will be much higher, even though everybody is more patient. So these are again real visualizations of real experiments. On the left, you can see like a traffic scenario, which is kind of a crossing, like a crosswalk going through. You have a random target on the other side, and you have to go there and avoid collisions. And on the right side, you can see these kind of package delivery, kind of central distribution where you have the same target for all the drones, and they have to queue patiently and wait for each other, and as soon as they are in the queue, they have to go. So you can do these kind of things. And this is kind of a footage of 30 drones doing these autonomous traffic experiments. And this is really, it's only 30, but also already something that it's really totally impossible to do with human operators. So if you ask if you ask two guys to drive two drones efficiently and not collide with each other, they already won't be able to do it because they don't see in 3 dimensions. And with these algorithms, you can actually have many drones fly together at the same coordinated dense airspace and avoid collisions by local communication. And this is a third project we are we were doing for one publication only, which is again a bio-inspired kind of thing, the collective chase and escape. Actually, we were not going too much into that because it's like too military oriented, and we didn't like that much. But this is another like kind of example of what nature in collective phenomena is good of. When you have these predator and prey systems, there are some very interesting aspects how they do it, and very interesting structures and cooperation between the agents. What you can learn and copy, and then you can design artificial chasing systems as well. Maybe it can help for your nets as well to have multiple agents from all sides, and then you can have the net dropping from the wind direction. Okay, so this is kind of the end of my talk. Just to relax, I will show you some examples what we do with the drones. We have a little company as well with which we are trying to use these kind of swarm use cases, and the most trivial one is the light. You said that the atmosphere of this conference is related to beer, so this is a big beer bottle with depicted by drones, and we do all kinds of shows with human drone interactions and paint on the sky with drones, and it's actually very. We work together with artists who are sculptors and creating sculptures, and they say that they usually like in 1 month they have like 500 people watching their sculpture, and it's actually quite an interesting feeling to have, for example, 500,000 people watching a drone sculpture and looking at the latest technology. So it's quite like inspiring to do this as well. And we are trying to do some very funny and also kind of dangerous stuff. So for example, fireworks launched from a drone. It looks really nice, but nobody allows that so far, but it's fun. So some of the financial support that we get right now, and probably this is the most complicated slide I was talking so far. So this is a big team. On the top you can see the department, and the ones who have like a red arrow are the ones from the department who are working on the drone thing, and here the green names are the ones who are actually active. We are kind of a small group, and the drone is not really the focus of our research, but there are some very nice people who are working on it. So also some publications I was talking about. So thank you very much for your attention.
Thank you very much, Gábor. And now we have 5 minutes for questions. So please, if you have some, we can use few. Okay? I see 2 people. You are the first.
Hi, sorry if I didn't catch it. When you were showing the testing with the actual real drones, could you confirm which method you use for self-localization and which method are you using for then sharing the information? Like which type of communication technology are you using for that?
We used GPS. Everybody had an onboard GPS receiver, so they know their absolute position, and they create an ad hoc Wi-Fi network, and they broadcast their own position and ID, and the others get these messages continuously from each other. So they know about everybody's absolute position and velocity.
Okay, and just out of curiosity, do you try to simulate that as the errors that could come with that when you do the simulations?
Yes, you mean communication errors? Or, sorry?
Yeah, exactly. Like any communication, certain things that could happen because
yeah,
I don't know.
So what is like usually all these errors and everything that comes in the outdoor experiment are always against us, but this characteristics of the communication is actually helping the system. So the power when you emit a signal, the power decays with distance with square, like with the second power of r. So it's with the square of the distance. It means that that actually you can emit a lot of signals because it will be decayed and it will disappear at a large distance. And actually, since we have a flocking algorithm that works only locally, all the interaction routes are local, it doesn't matter if the ones far away doesn't get it because you need to communicate only with your neighbors. So you emit a lot of signal, you don't get bandwidth problems because it decays with distance, but the local communication is very strong because there you have a lot of signal. So in the paper there are some measurements about it, but like below 40 meters we get like almost all the messages going through, and above that it's decaying, but it doesn't matter because it's a local interaction anyway.
Thank you.
Thank you so much for your great presentation. It was really impressive. I just
Hold it
had a,
very close, please, to your mouth. It's working, just hold it close.
okay. Thank you so much for your great presentation. It was really impressive about how you did that. I just had one question about the way you have allocated the velocity. You said the velocity desired had four components. Could you go back to that slide? One component is related to the repulsion. The other one is related to the...
Yeah.
Okay. Okay.
Like this one?
Yeah, this one. So, as you can see in that summation, how many components are there in that summation? Because
Okay, yeah, this is a kind of a simplified equation. So the summation always goes for all the neighbors around within the communication range.
so for all the neighbors, but
Yes,
then that
yes.
is not what happens in the nature. Because in the nature, we just have local information.
I know, but as I said, just for the previous question, you can include everybody in your local communication range because it decays, so it will be a limited range anyway. So if you want, you can limit it to a spatial distance artificially, but it's generally the same. So yeah, I
So
mean,
did you actually try to simulate it in such a way you had
yeah,
restriction in the number of neighbors?
yeah, in simulation, we change the communication range and see everything with very small and very large, and it actually works because all the information is spread locally. But I also think that when you do an artificial system, it's very good if you learn from nature, but you don't have to stick to the rules of nature. So if you have a communication that is better than the natural one, then why not use it? So.
Okay. So regarding the communication, what did you use? You said that you used some portable communication.
We started with like XB modules, the same as you use for the RTK, and then now we just use a very simple like Wi-Fi module, and it's just a simple like 2.4 gigahertz Wi-Fi ad hoc network, so nothing special really.
So the Wi-Fi module is being carried by the autonomous agent?
Yeah,
or?
it's like a small module. It's
Small
carried by
module.
the drones, and they emit a status signal like 10 times a second, and
Okay.
so you can build this system now out of the box, like with very like ready-made components.
Okay, thank you so much. That's so impressive.
Hello, thank you for the presentation first. One question about the communication part. You were saying every single drone has a GPS and it knows its specific location and broadcasts it to others. So are other neighbors also broadcasting the location of their neighbors, or just
No,
their own?
everybody just their own.
Just their own. So
Yes.
local interaction is actually creating this scalable.
Yes. Yeah, it's just so there's no mesh protocols involved or messaging like on routes. It's just local, really local.
Oh, okay.
And also it's just broadcast, so not TCP/IP but UDP type communication. So you just broadcast it,
Send
and if your
around
neighbor
and just-
receives it, it receives it. If not, then the next one comes. So actually, if you create a mesh network, then you also, if you increase the size, you get all kinds of oscillations and delays,
that
and we
was
don't
my
want that.
question.
So we want to stick to the local and just broadcast type communication, and then it's scalable.
Okay, thank you.
Thank you for the presentation. One question, is there any guarantee of collision avoidance among the agents, the drones?
Actually, it's a good question, there's no guarantee.
Yeah, because I noticed that in your simulation with over 300 drones, and at the left corner, there shows a lot of collisions.
Yeah, I mean, in the simulation we are counting the collisions, and this is like for 300 agents, this is the best we could get, like a definite collision like probability, not too high, but there is something, and that's why we were going for even better model. We are going for better models now, but you can never really, in a stochastic system, it's impossible to reduce the collision probability to zero, because you have not correlated noise, you don't know what is coming next, and it can happen that a random noise interferes with your system. So there's no guarantee for zero collision probability, but you can reduce it to such a low rate that it's acceptable.
Okay, thanks.
If not, thank you again, Gábor, and I have also a small present for you. So thank you for coming.
Thank you
a lot.
very much.
Now we are going to have the second coffee break. So again, the same, or I don't know if the same food, but the same style of providing food is there. And after that, we have the presentation. We have all PDFs already downloaded, and just ask the presenters to come a bit earlier to prepare everything. Thank you.